Hello students, in this video we are going to see about dynamic circuits. In this dynamic circuits, clocked PMOS pull-up is used. There are two modes are available, one is precharge and other one is evaluate. This dynamic logic circuit provides similar results as in static circuits while avoiding the static power dissipation. With the addition of a clock input, it uses a sequence of precharge and conditional evaluation phases to realize the complex logic functions. Dynamic circuits are fastly used as circuit because they have lower input capacitance and no contention during switching. Dynamic circuits operation is divided into two modes. One is precharge. During precharge, the clock that is represented as phi is 0, and while using evaluation phase, the clock is 1. Let's see the construction of N-type dynamic circuit. During precharge, the clock phi is 0, so the clocked PMOS is on and initialize the output Y as high. During evaluation, the clock phi is 1 and the clocked PMOS turns off. The output may remain high or it may discharge low through the pull-down transistor. We all know the given input to the PMOS is 0, the PMOS will on and gives the output as VDD. While the NMOS is connected to, while the PMOS is given as a 1, the PMOS will off and the previous state output will discharge to ground. So, during precharge, evaluate, and then precharge mode is draw like using a square waveform. Next, we all know during precharge phase, the clock is 0. Okay. Then, what if the input is on during precharge? The question is, what will be done when the input will be 1, which is given to PMOS during precharge phase? Contention arises because both PMOS and NMOS will be on. Use series evaluation transistor to prevent fight. Okay. Then the new technical content as FOOT is introduced here. Due to logical effort, the speeding of the transistor will increase. Here, the FOOT is nothing but when the input cannot be guaranteed to be 0 during precharge, an extra clocked evaluation transistor can be added to the bottom of the NMOS stack to avoid conflict. The extra transistor is sometimes called as FOOT. Okay, the size of the FOOT can be increased relative to the other NMOS transistor to reduce logical effort. Okay, when the FOOT is added, the logical effort will be high. If the FOOT is not added, the conflict may arise and the logical effort may low. While see this image, the dynamic circuits are unfooted. The inverter NAND 2 or NOR 2 inputs gate logic input be 1/3 or 2/3. While we give FOOT circuits under the dynamic circuits, the logical effort may increase. So, let's see about important properties of dynamic circuits. The logic function is implemented by the NMOS pull-down network. So, we use the pull-up network to drive the circuit. The number of transistors is N+2, which is lesser than the static circuits. In the static circuits, for a single input, we can use 2 NMOS and 2 PMOS. But here, we can use the number of NMOS transistors to implement the logics, and one pull-up network and one FOOT transistor can be used to realize the dynamic circuits. The sizing of the PMOS precharge device is not important for realizing proper functionality as seen in the above point. Hence, it is non-ratioed. It conserves only dynamic power. At the first itself, we can know While avoiding the static power consumption, the dynamic logic provides the similar results as in static circuits. The logic gates have faster switching speed because the logic effort is higher when foot is introduced into the dynamic circuits. Then we go for monotonicity requirement. The precharge transistor width is chosen for twice unit resistance. It reduces the capacitive load on the clock and the parasitic capacitance at the expense of greater rising delays. Footed gates have higher logical effort than the unfooted gates, as we all know. Next, why the monotonicity requirement is needed. A fundamental difficulty with the dynamic circuit is the loss of immunity and timing restriction on the gate input. While a dynamic gate is in evaluation, the input must be monotonically rising. The figure demonstrates the waveforms for a footed dynamic inverter in which the input upsets monotonicity. Here, during precharge, when phi is equal to 0, the output is in high, as we all know. When phi is equal to 1, the input A is equal to 1. The output is low. The pull-down network is turned off. The precharge transistor is off, causing the output to float. Output continues to remain low until the next precharge step. The input must be monotonically rising for the dynamic gate to compute the correct function. This is the requirement of monotonicity in dynamic circuits. The dynamic gate require monotonically rising inputs during evaluation, which means 0 to 0 or 0 to 1 or 1 to 0, but not 1 to 0, which means there is no falling edge during the evaluation